Hello and welcome back to Precalculus1, section 2.6, rational functions. So, rational functions are functions which divide polynomials. So, a rational function is a quotient of polynomial p of x divided by the polynomial q of x. Some of the examples of this would be, let's say, 2x plus 1 divided by x squared plus 7x minus 3. 1 over x is the cheapest possible case you can have. And then maybe 3 over x squared minus 1. I don't know. Whatever you put technically works, as long as it's a polynomial divided by polynomial. X to the fifth plus 3x squared minus 7, whatever. So these are examples of rational functions. We are going to first talk about rational function 1 over x. Then we are going to define asymptotes and learn how to deal with those and how to get those. And then we can talk about general cases and learn how to graph them without the calculator, which is where the two-part exam comes in if you guys want to have an exam. So we start about considering, so let's consider function f of x equals 1 over x. We want to learn everything there is to know about this function. Well, this is one of the basic standard functions, and you are supposed to memorize its graph, its basic graph, just like you memorize square root of x, x squared, and those other basic graphs. And this gets added to the list of basic graphs. So I believe earlier we had 7 of them, right, including absolute values, square root, linear line, constant line, x cubed, x squared. Now we are adding 1 over x as a basic function to be memorized, as we are going to shift it left, right, up, down, and do all of the cool stuff. So the basic graph for this function looks like this. So it follows these axes and gets ever closer to them without ever crossing. So now that we have the graph in front of us, we can start asking just regular Precalculus1 questions. Question number 1 is the question of domain. What can you tell me about the domain of this, looking at it? I'm sorry? Almost there. Yes? Not including 0. So domain is negative infinity to positive infinity, not including 0. And we are going to write that by kicking 0 out, using parentheses. So domain is from negative infinity to positive infinity, excluding 0. How about range? Same thing, very good. You can see that it works the same, except it's vertical. Not including 0, everything else is just fine. Great. How about X-Intercepts? None. A Y-intercept? None. So we see that the function never cuts through x-axis to create x-intercept, and the function never cuts through y-axis to create y-intercept. We can see that the function is always decreasing. So our entire domain is a decreasing part. And we also see that it has interesting end behavior. End behavior on the left and the right is tending to 0, right? Remember that end behavior for polynomials was either that, or that, right? It was always going to one of the infinities, positive or negative, for end behavior. Well, now for end behavior for this particular function, you see that these arrows, they actually tend to 0. So they are tending to y equals 0. And now, with this graph, for the first time, we are introducing the concept of an asymptote. Now, asymptotes are linear lines which functions follow, obey, or in some cases not cross. So the two asymptotes that we have in this particular case would be a horizontal asymptote at the x-axis and the vertical asymptote y-axis. So x equals 0 and y equals 0 would be these asymptotes. And the asymptotes are these lines which functions follow, and as I said, in some cases do not cross. So looking at the, so now we're going to take a look at definitions of these so that we can work out some problems. So vertical asymptotes. For the most part, in Precalculus1, we have the vertical asymptote when denominator is equal to 0. So vertical asymptote is the line whose slope is infinite, and that's what we obtain when we try to divide by 0. So for the vertical asymptote, we will set denominator equal to 0. And whatever points we find, if we find any, we have a vertical asymptote at that point. Now, I need to make sure that you know that your function needs to be in the lowest terms. So you have to make sure that everything is canceled. That could be. I'll show the example of what I mean later. So vertical asymptotes, we set denominator equal to 0. So say you have f of x as x minus 2 over x squared plus 1. Sorry, x squared minus 1. We set denominator equal to 0. We solve it, and we get x equals plus minus 1. This means 2 vertical asymptotes. Two. There's one at positive 1 and one at negative 1. So for this particular function, I would draw a vertical line dashed like this at negative 1 and vertical line at 1. Now I'm not going to fill in the function. That's later in this class. Right now we are learning just how to obtain the horizontal and the vertical asymptote. So now that we know that we obtain the vertical asymptote by setting denominator equal to 0, we can go back to our original function and say that the vertical asymptote is at a equal x equals 0, right? Because when you take the denominator and you set it equal to 0, you get just x equals 0, and you're done. This is the basic function, so that's why it's so easy. So we have a vertical asymptote at x equals 0. Vertical asymptotes are the vertical impenetrable lines that functions can never cross. Vertical asymptotes can never be crossed. And you obtain those by, once you have reduced function, you can set denominator equal to 0, and you have your vertical function, your vertical asymptotes. Now, what am I talking about, this reduced function and so on? Well, your function could be given as, and we discussed this in calculus in much greater detail, your function could be x minus 3 divided by x squared minus 9. And if you go and set x squared minus 9 equal to 0, you will come up with negative and positive 3. However, one of them is not asymptote. So you have to be very careful. What you have to do first, before you set denominator equal to 0, you have to factor everything and make sure that the rational function cannot be simplified any further. And if you see over here, x minus 3 cancels, and the actual function that we should consider for asymptote is just 1 over x plus 3. And that, for our vertical asymptote calculation, provides a single vertical asymptote at negative 3. The positive 3 is not a vertical asymptote. Now you might ask, what is the one? Because we should have an original problem, right? Well, it's the open circle. That's what it is. So the function would look normal and just have open circle at that point. Well, we discussed those actually in calculus to the greatest detail. In PreCalc, we try to stay with the problems that are obvious and straightforward to do in terms of vertical asymptote. But you need to have this in the back of your mind just in case, that the function has to be in the lowest terms, right? It has to be canceled the most you can, and then whatever is left over is to be considered for asymptotes. So this problem, even though it looks like it has 2 asymptotes, it actually has only 1, because one of those canceled. Previous problem, you can't cancel x minus 1, x plus 1 with x minus 2, so both of these were kept as asymptotes. How many vertical asymptotes can you have at one time? You can have any amount of them. We have examples that have no vertical asymptotes of rational function, because when you set denominator equal to 0, it doesn't return any answer. And that was the one with the plus that I tried to sneak in, and then I realized. So let's say you have x plus 5 divided by x squared plus 1. You see, x squared plus 1 equal to 0 has no solution in a real plane, therefore no vertical asymptotes. So in this case, x squared plus 1 equals 0 has no solution, which implies no vertical asymptotes. So how many vertical asymptotes could we have at one time? You can have none. You can have 1, 2, 3, 4, whatever amount, all the way to infinitely many. Next year, you are going to learn next semester, you're going to learn trigonometric function called tangent of x. Tangent of x has infinitely many vertical asymptotes. And so does cotangent and cosecant and secant. So 4 out of 6 trigonometric functions have infinitely many vertical asymptotes. And sine and cosine have none. So we can have 1 vertical asymptote, 2, 3, 5, infinitely many, or none of them. So that's the story of vertical asymptotes. Now, we define horizontal asymptotes. Horizontal asymptotes are horizontal lines which functions have to obey at infinities. These can be crossed by function. And that is something that you have to accept immediately. Vertical asymptotes can never be crossed. You cannot puncture through vertical asymptote. But horizontal asymptote, yes, you can cut through horizontal asymptote. And again, the reason for these things is going to be in Calculus 1, Chapter 2, when we talk about limits, infinite limits and limits at infinity. And that's where we discover why these things happen. And that's, short while for you. I have 1 course in between. So horizontal asymptotes are asymptotes that are obeyed at infinities and can be pierced locally. So these horizontal lines are obeyed, I guess, at positive, negative infinities and can be crossed by a function. What this means is that the horizontal asymptote has to be followed by the function as the function goes to infinity, but you can cut through it locally at 7. You can cut through it if you need to, if the function is cutting through it. Now, what you have to memorize are 3 cases of where these and how these things appear. You are going to have your rational function, r of x, to be coefficient a, I'll put p of x, divided by b, q of x. So you have a leading coefficient, a, and then a polynomial, which is in the numerator. And then you have the leading coefficient b times some polynomial in denominator. Here are the rules. You have to memorize these. Rule number 1 says, if degree of p is larger, smaller first, is smaller than the degree of q. So if degree of p is smaller than degree of q, horizontal asymptote is at y equals 0. So if degree of p is less than the degree of q, your horizontal asymptote, which is a horizontal line, is y equals a number, so it's y equals 0. Second thing, if the degree of the polynomial p is the same as the degree of polynomial q, horizontal asymptote is at y equals a over b, ratio of those coefficients. And finally, 3, degree P larger than degree Q, no ha. No horizontal asymptote. So this is what you must know. Now within this, the rule number 3, we have a whole new class of asymptotes, which are called slant asymptotes. So what I'm going to do is I'm going to break off this rule 3 and write down slant asymptote. And slant asymptote says, slant asymptote is y equal mx plus b. So it's some linear line that it's slanted, it has a slope, right? That's what it is. So when do you have a slant asymptote? You have the slant asymptote when the degree of P is equal to the degree of Q plus 1. Immediately example for something like this would be f of x equals to, let's go with x to the 4th minus 2x squared minus x plus 1 divided by x cubed plus 9. You see that the highest degree in the numerator is 4, and the highest degree in the denominator is 3. So 4 and 3 are 1 unit apart, which means that you can perform long division and find that slant asymptote. So how do you find the slant asymptote? If the condition is satisfied, use long division to find the line. And these are all the rules for asymptotes. So for vertical asymptotes, make sure that the problem is factored and simplified as much as possible, and then set denominator equal to 0. For horizontal asymptotes, you must memorize 3 rules. If the degree in denominator is larger, it's at 0. If the degrees are the same, it's at a over b, which is the front coefficients. And then if the degree in the numerator is larger, you don't have horizontal asymptote. But if it's larger by 1, then you have a slant asymptote, which you have to compute. So now we're going to take a look at examples for this. So let's first figure out how for a few examples. Example number 1. F of x equals 3x squared minus 4x cubed plus 9 divided by x squared plus 7. What can you tell me about horizontal asymptote? Very good. No horizontal asymptote. We have a slant. You can't have slant and horizontal at the same time. They are mutually exclusive. So if you take a look at the leading terms, I try to hide the leading term in the middle because I'm a terrible person. But you picked up on it, which is great. You know that the leading term is the one with the highest exponent, no matter which position it takes in the polynomial. So you see that the degree on top is 3, and the degree on the bottom is 2. So top has the higher degree, which means no horizontal asymptote. So degree of P is larger than the degree of Q, which implies no ha. No horizontal asymptote. Now that is the rule that you have to memorize. You might be lost right now. but you're lost because you don't know the rules. Once you know the rules, right? There's like this, I read about this new rule now. If you are passing a tractor or a farm equipment on the road, you have to match their speed first and then pass them. You can't just pass them, apparently. That's a new rule, and you can pay money if cop sees you just passing them, which is, But yeah, so there is the rule right there. You learn the rule, and then you don't get into trouble. So you simply look at there are no calculations over here, guys. You use your eyes and you look at it. And you either know or you don't know. So here's the next example. Example number 2. Oh, maybe I should say yes on SA, but we'll deal with the rest. Big slant asymptote, SA. You have ba, ha, sa. Vertical asymptote, horizontal asymptote, slant asymptote. So va, ha, sa, whatever that means. Drink some water. Drink some water. Here. I'll make it closer. So, f of x. Right, good. Let's say you have 3x cubed minus x squared plus 8x minus 1 divided by 4x cubed plus 1. What can you tell me about horizontal asymptote situation, looking at 3 rules? That's all I heard. Good. So degrees are equal. Both are 3 and 3, which means we use front coefficients, leading coefficients. And that's what? 3 over 4. So, ha at y equals 3/4. Oh, if you write this, I promise 0 credits right away. If you write this, this has no meaning in mathematics. If I see this on any of the tests, it's 0 immediately. That is no. Ha equals 3/4 has no meaning. Horizontal line is y equals a number. So note that I say horizontal asymptote at, and then I write the equation y equals 3/4. So this is where you get points. If you write ha equals 3/4, you missed it. Same goes for va and sa. Oh, I almost forgot. Didn't we have the initial problem? Do we have a horizontal asymptote here? Anyone? Y equals 0. Why? Now, what's the denominator? What's the degree in the numerator? 0. Yes, 1 can be written as x to the 0, and the 1 on the bottom is x to the 1, 0 less than 1. Awesome. So, this is the situation where the degree in the numerator is smaller than degree in the denominator. So, ha at y equal to 0. And we go all the way back to the original problem that we were considering, and we say ha at y equal to 0. Now you can see these two that we just discovered, right? There's your horizontal asymptote, y equals 0. It's just a straight line. Just your eyes are no good. And vertical asymptote, your x and your y axis. Good. can I make these asymptote questions hard? And the answer is hell no. Because to figure out your vertical asymptotes, you are setting the polynomial in denominator to 0. You are looking for zeros of the polynomial in denominator. Well, that's what you had at the beginning of the class and the whole last class. You know how to find zeros of polynomials. If it's obvious, cool. If it's terrible, well, you can still do it, right? You do the pers and do all that stuff. So you take the denominator and you set it equal to 0, which creates this type of a problem. So if I just give you x squared minus 4, yeah, you know immediately answer it plus minus 2 and you move along. But if I give you anything else, right, that has more sustenance to it, you will unleash the knowledge from previous sections and find all of the zeros. Every real zero you find is a vertical asymptote for the problem. For the horizontal, you must memorize 3 rules. You cannot tell me that the problem is hard because you didn't memorize the rules. That makes no sense. So no, I can't make this hard. If you know how to find zeros, you know you set denominator equal to 0, great, you have vertical asymptotes covered. When you memorize the 3 rules for horizontal, that one is even easier. 0 calculations. You just lose your eyes and you look at it. And you say degrees higher on top or bottom, and you just use appropriate rule. And you're done. The only one that tends to be annoying is the slant asymptote, because you have to do long division of polynomials. If the degree in the numerator is by 1 higher than the degree in the denominator, you have to use long division of polynomials to figure out what the vertical asymptote is. Sorry, slant asymptote. And the good news about it is that you only have to do 2 steps. No one cares about a remainder and these kind of things. You will only work out the first term and the second term because that's your mx plus b. So for the slant asymptote world, also known as SA, right? I mean, you can spell it every time. In some books, if you're reading other books, and they're known as oblique asymptotes as well. So you might run into that word, the word oblique. Oblique asymptote is the slant asymptote as well. All right, so let's say you have f of x equal to 3x cubed minus 4x squared plus 9x minus 1 divided by x squared plus 4x plus 3. All right, so now the question is find all asymptotes. You can work out that vertical asymptotes exist because you set denominator equal to 0. I hope just by looking at it you see that the answers are 3 and 1. I mean negative 3 and negative 1. So you know you have 2 vertical asymptotes because when you factor denominator you get negative 1 and negative 3 as answers, so 2 vertical asymptotes. But we are interested in horizontal and slant, primarily in slant. Horizontal asymptote doesn't exist because the degree in the numerator is bigger than the degree in the denominator. So that is when the horizontal asymptote does not exist. But the degree is bigger by 1, which means yes on SA. And to find it, we just use polynomial division. Just. So 4x squared, sorry, x squared plus 4x plus 3 divided into 3x cubed minus 4x squared plus 9x minus 1. X squared goes into 3x cubed 3x times, and then multiply back standard stuff, guys, nothing new. These guys die. We have negative 16x squared. I don't even have to copy the rest because we are done. X squared goes into negative 16, x squared negative 16 times. No one cares about the rest of the problem. Slant asymptote is defined as y equal mx plus b, and you already have your y equal mx plus b, so your SA, slant asymptote, is at y equals 3x minus 16. That's it. So you only have to do one full step, and as soon as you subtract these, you don't have to bother with the rest. The first term goes into that negative 16 times mx plus b, done deal. You're done in 1.5 steps. So that's the good news about slant asymptote, that you don't have to divide and get the remainder and other stuff because we don't need it. For the same problem, if I'm to push for vertical asymptotes, the denominator x squared plus 4x plus 3 equals 0 is factored over x plus 3, x plus 1. And we have x equals negative 3, x equals negative 1, and both of those are vertical asymptotes. So quick algebra solves the question, and we can also say no ha, right? No horizontal asymptote because we have slant. You can't have slant and horizontal. So at this point in time, I would like to just find a problem in the textbook. And have you guys consider all three asymptotes, which is going to be your exam question. There will be exam question dedicated, well, the problem that you're going to see now. It's just going to be a different function, but all right. Or maybe 2 examples would be good enough. Find all asymptotes. You have 3 kinds here. I'm going to write so va, ha, sa. You have to consider all of them. The first example you guys can work on is, let's say, example 34. Looks good enough. Age of x, whatever, is x plus 6 divided by x squared plus 2x minus 24. Can anyone tell me a vertical asymptote situation? I'm sorry? 4, -6. Anyone? Vertical asymptote situation. Hello? Aha! It reduces. So we actually have only one vertical asymptote. Good. So this is x plus 6 divided by x plus 6, x minus 4, and these cancel. So we are left with 1 over x minus 4. So when I, for vertical asymptote, set x minus 4 equal to 0, I get x equals 4 as the only vertical asymptote in the game. Perfect. How about horizontal asymptote? Yes? Y equals 0. The degree in the numerator is 1, which is less than the degree in the denominator, which is 2. So P less than Q. We have Y equal 0. So if we have horizontal asymptote, can we have a slant asymptote? No. They are mutually exclusive. So if you have one, you can't have the other. We do have horizontal asymptote at 0. Therefore, that's that. All right, one more quick example, and we are going to move on with our lives. That's going to be 35 good enough? Ooh, 43. Again, find all asymptotes here. All. Right. So f of x equals negative 3x plus 7 divided by 3x plus 5. No, negative 2x on top. Negative 2x plus 7 divided by 3x plus 5. All asymptotes. All right. So what is the vertical asymptote? Negative 5/3. Good. Any horizontal asymptotes? Negative 2/3. Good. Degrees are the same, so negative 2/3. You just look at it. How about slant asymptote? Good. You can't have horizontal and slant at the same time. What happened? Yeah. Well, that you can see that in rules, right? The rules say, see, slant asymptote is the part of 3. So 1 and 2 is where asymptote exists. See, y equals something and y equals something. And then over here, no horizontal asymptote, and that's where the slant shows up as a subcase. So we see it in the rules that it's one or the other. You either have something, you either have horizontal asymptote, or you don't. And slant asymptote is the subcase of where you don't have horizontal. All right, let's open the gates of hell and peek inside, see what's cooking. Graphing rational functions. Another exam question. There are 3 exam questions in this section. Graphing rational functions. We'll start simple and then upgrade. There is a shopping list of things that you have to get, which will help you to draw a graph without the use of graphing utility. I'm encouraging you to use graphic utility or Mathematica because to check, right? Because that software can graph this quickly. So what is the shopping list of things that you must get to graph? So need to get. Number 1, domain. Number 2, X-Intercept. Number 2, Y-Intercept. Number 4, Va. Number 5, Ha. Number 6, Sa. And then number 7, if needed, additional point. So this is your shopping list of things. The first 6 are necessary. And this is half of your Calculus 1 list. So you learn this now. When you go to Calculus 1, Chapter 4, which is what I'm going to teach this Saturday, if you tune in, you will see this list augmented with another 7 things, calculus things, derivatives, and other stuff. And that will be the... So you are learning technically half of the problem right now. Example. Graph f of x is equal to x minus 3 over, let's say, x plus 5. Right. Number 1, domain. What is the only point that we are not allowed to use? We can use 0. 0 plus 5 is 5. Negative 5. So the only bad point is negative 5, and that's what breaks the domain. So negative infinity to negative 5, union, negative 5 to positive infinity. Number 2, X-intercept. How do we find X-intercepts? Is the skill from algebra class. Set y equal to 0. So set the entire function equal to 0. So we have x minus 3 over x plus 5 equal to 0. When you cross multiply, you get x minus 3 equals to 0. And you get x equals to 3. Aha! X-intercept at 3, 0. How about y-intercept? Y-intercept, anyone? Set x equal to 0. So when you set x equal to 0, you get 0 minus 3 divided by 0 plus 5, and we get negative 3/5. So 0, negative 3/5 is the y-intercept. So far, this was all algebra, right? Well, no, domain is PreCalc. But number 4, VA. Do we have any vertical asymptotes? Any vertical asymptotes? Yes? X equals negative 5. You take the denominator, set equal to 0, and we get this one. Number 5. Do we have horizontal asymptote? Do we have horizontal asymptote? Yes. What is it? 1. Number 6. Sa? None, because we have horizontal. I'm not going to compute any additional points because I might not need them. Let me graph what I have, and maybe I can connect the graph without computing extra stuff. So we start with the coordinate system xy, and then we place all of the points and all of the asymptotes that we know. Oops. So we have a vertical asymptote at negative 5. All right, 1, 2, 3, 4, negative 5. So negative 5. We have a vertical asymptote at negative 5. We have 0, negative 3/5 as the y-intercept. Oh, y equals 1, horizontal asymptote. And we also have 3, 0. I need you to stare at this picture a little bit and notice that the two asymptotes partitioned the entire space into 4 regions. So ignore axes. I understand that axes also divide space into 4 regions. But for rational functions, these asymptotes are guides where the function goes, not your x and y axis. So you have to train your eyes to see the dashed lines and ignore x and y. So now, if I go and erase these 2 lines, this is actually what guides your graph. And in my humble opinion, it should be common sense to realize that there is a line that goes through these 2 points in this quadrant following 2 asymptotes and curves just like 1 over x did. So I would label that common sense because you have 2 points there. You already have 2 points through which the function has to go, and you know it has to follow asymptotes because that's what functions do. So it should follow the y equal 1 asymptote, go through both points, bend, and follow the -5, x equal -5 asymptote. So we ignore coordinate axes and we start looking at the asymptotes to guide the graph. Now I will put these asymptotes back in the game, and I will draw the graph now. So it's going to follow, go through these, and then bend down to keep following the axis. So this is the first part that it's easy to draw. And then we have one more to draw. Remember that your domain was from -infinity to +infinity, and it didn't work in -5. So -5 is the point that doesn't have y value anywhere. Great, that's where the vertical asymptote is. That all matches. But remember that there is another piece that we have to draw to the left of the vertical asymptote, because the domain is from -infinity to -5. So there has to be a line in there. Also, make sure you don't stack lines on top of each other, because it's not a function, right? It fails vertical line test. Once you draw a piece, you can never put another piece above or below. That just tells me that you are completely clueless in this class. The definition of the function says, for every input x, a single output y. You are never allowed to stack up functions on top of each other, because it stops being a function. It fails vertical line test immediately. So you can go piece and then the next piece and the next piece, side to side, never on top of each other. So we know now that, again, 2 reasons provided. We know that we need to draw another piece either here or here. So you have those 2 right parts. And you are not allowed to draw anything in here, because it would stack on top of the red one, and it would make everything not a function, and the whole problem goes to garbage. Now the question is, and we know that they follow asymptotes. The question is, do I draw that piece like this, or I draw the piece like that? Right? If you think enough about this and you're interested, you would quickly come to conclusion that the one on the top is the right choice. Because you only calculated one X-intercept and it's used up. You see that this red line, in order to follow the horizontal asymptote, has to pass X-axis again, creating another X-intercept which you don't have. The only X-intercept which you found, you already used up. And you do not have another one for the bottom piece. So that should be enough for you to realize that the other piece of the graph is here. But let's say that this analysis is way too crazy. What you are going to do is you are going to compute additional single point. You pick any x value to the left of -5, say -6. You draw the point, whatever you get for the y value, you draw that point, and since the asymptotes partition space, you draw the line through that point. So let's say that the entire story about additional X-intercept made 0 sense. You will say, okay, I don't know where the other piece is because I have no information, so let me just compute f of -6. -6 is right there. Now, that point will be either here, let's say, or there. And then I know to draw and follow asymptotes through that point. So what was the function? It was -2 times -6 plus 1 divided by 3 times -6 plus 5. That was original function. So 12 plus 1 is 13 divided by -18 plus 5 is -13. Oh, what am I looking at? I have no clue. All right. Oh, no, this was a previous problem. Okay, what was the function? X minus 3, x plus 5. X minus 3, x plus 5. Thank you. So that's -9 over -1. It's 9. So you see that y is 9. You have a point -6, 9. Well, that's definitely the piece in here. That's how you graph rational functions. You obtain the 6 point, and if you need to, compute extra stuff. I still like the other argument much better. The piece which says that these lines must follow asymptotes. So it's either the top or the bottom. Has to be one of them because the domain says all the way from -infinity up to -5, there is a line somewhere. So it's either here or there. We eliminate the bottom one because we don't have the X-intercept for it. That's why we eliminate that one. Or you can do additional point and you compute. All right. Next example. That's what we do. Problem 62. You got this. You got this. F of x is equal to 4x squared divided by x squared minus 9. Get the shopping list done, and then figure out if you need additional points. Did you guys figure out that once you figure out the domain, you have your vertical asymptotes right away? Right? Because vertical asymptotes plus domain have to make up 100% of the stuff. So, number one, domain. We break at -3 and +3, so -infinity to -3, union, and -3 to 3, union, 3 to infinity. This immediately means that your vertical asymptotes are -3 and 3. 2. X-intercept, set y equal to 0, which means we set entire problem equal to 0. When you cross multiply, you immediately lose denominator because x squared minus 9 is multiplied into 0 and just dies there. When you divide by 4 both sides, you get x squared equal to 0, and you square root both sides, you get x equals 0. Nice. X is 0, y is 0. You have the origin. Now that's y-intercept at the same time. Right? The origin is the only place where you have x-intercept and y-intercept coincide. If you go and you compute y-intercept, you will quickly see that. Because you set x equal to 0, and you get 4 times 0 over 0 minus 9. 0 divided by -9 is 0. So 0, 0 again. So that's an important point. Number 4, va. That's x squared minus 9 equal to 0. We already discussed that. We get plus and minus 3. So 2 vertical asymptotes. This time. How about ha? Y equal 4. Very good. We have the same exponents. If the exponents are the same, it's the ratio of fresh coefficients, of front coefficients. And I just had food before the class, so so front coefficients, which is 4x squared over x squared, just 4 over 1, which is 4. How about SA? Slant asymptote? Because we have horizontal. You can't have both. One or the other. Or none. You can have none of those. Is this enough for us to draw a graph? All right, let's see. This one is the y-axis. This one over here is the x-axis. I have a vertical asymptote at -3. Vertical asymptote. Should I use red and... Yeah, let me color code the way I did earlier. So that's that, and then I have the blue one. At y equals to 4. Perfect. And all I have is a single point. 0, 0. This is all of the information I have. It's trouble now, because I don't have any information. Well, I actually have everything I need for the left and the right. How many x-intercepts do I have? And are they here or here? Are they? So where does the line, where the line must be? On the top, right? So we know that we must have here and here. That's just common sense. Because the other alternative is to have it here, but we don't have the x-intercept for it. So it can't be there. Again, the line is either here or here. Since we do not have these x-intercepts, it cannot be there. And we're done. Now, for this one over here, there are options. The function can do this, or it can do this, or it can do this, or it can do this. And we don't have any information which of those four it is. So you can have this, 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 or this. It's one of those four. Which one? U shape like this? Why? Because you guessed, because it's x squared. Well, tough luck, it doesn't work that way. You can't say, oh, it's x squared. So it's because that x squared is divided by another x squared, and you have 4, right? So you have to pick points in this case. You have to compute f of -1, and you also have to compute f at 1. And then you will know. When you have those 3 points line up, because the point is either going to be here or here. And then you know which way to go. So f of -1. F of -1 is going to be 4 over -8, which is -1/2. That's below. And then f of 1 is also 4 over -8. It's also -1/2. Aha. Right? So we're using 4x squared, x squared minus 9. 4x squared over x squared minus 9. This is 4 times 1 over 1 minus 9, which is 4 over negative 8, which is negative 1/2. So I have a point, negative 1, negative 1/2. That's this point here, below x-axis. The other one, when you lose the minus signs, but because everything was squared, you get the same numbers. So now we see that all of these values are below right? All of these values are below, and that's the shape. This is the function. It will take a few of these to get used to it. You know, set aside about an hour and a half to work through these things. This is a standard question for the exam, right? That one or this one. It tests everything. Knowledge of asymptotes, knowledge of domain, x and y intercepts, and then graphing. Only if you need additional points, you will go and compute additional points. Next class, next week, we are going to start with 1 or 2 examples of this. But our chapter is over. Chapter 2 is done. Did we talk about the exam? So let me just add, so